Hello dear student, this is Devang Shah from LG Institute of Engineering and Technology under the LG University. So far we are learning about the combinational logic. From combinational logic we have defined the design from the truth table, then deduction of or deduce the Boolean function from the K-map method, and then finally we have carried out with the digital design that have a capacity to add 1 bit of information, capacity to add 3 bits of information, as well as subtract 1 bit and subtract 3 bits from together, right? So this is what about the combinational logic. There are so many different small discrete modules are available. We can define all those discrete modules as the kind of combinational logic where we can also convert one form of code into another form of code. So ultimately, in our previous sessions we discussed about the kind of conversion of BCD number into XS3, again the kind of conversion of binary number into BCD or binary number into XS3, or a kind of binary number into gray code, right? Same here, we have to realize those conversions using a digital circuits, right? So let's start with our first is called the BCD adder. Now what is the BCD adder? You just learn about the concept of this BCD adder, where you can find BCD adder is refers to a 4-bit binary adder that can add two 4 bits of words of BCD format, right? So BCD is always represented in terms of the 4 bits. So here your job is to find the output of the addition is a BCD format 4-bit output word which defines the decimal sum of the ended and the organ, and a carry is credited in case of sum exceeds the decimal value of 9. So from that we can be able to learn that particular terminology from this particular table, where you can find there are numbers from 0 to 9, right? And the corresponding BCD numbers I can consider as a from S0, S1, S2, S3, this sequence, and this sequence is represents the BCD sequences 8, 4, 2, 1, and C is called the carry, right? Now if there is a number from 0 to 9, there is no problem to convert binary number or a BCD number. So from 0 to 9 digits, see, binary looks the same, BCD looks the same, right? So your binary sequence is 0 0 0 0 and BCD sequence is 0 0 0 0 for a digit 0. Same way up to digit 9, your binary sequence is 1 0 0 1 and BCD sequence is 1 0 0 1, right? But once is from 9 to 10, see, you will see the difference of binary here, which represents decimal 10 or digits 10, is like 1010 in a binary, but in BCD each digit is represented by the 4 bits, right? So in BCD 10 is represented as 0001 and 0000, right? For sake of simplicity, we are taking 5 bits of information. So C is my carry if I consider, and rest of the position is like 0000. So here 10 in BCD is represented by 1 and 0000. Same way up to 19 you can represent like 1 and 10001, right? So you can define your logic here from the previous slide. You can check from the previous slide, from information here 9 is represented as 1001. If you add 6, see, in a binary information, since this represented in form of 1000, right? So this condition is very important condition here. So each time where any number is from greater than 9, you have to add plus 6 always, right? Clear everybody? So that's how you can convert any decimal number or digit into a BCD number, right? So for that we define a simple calculation here. If I want to add 6 plus 8, my answer is 14, right? But 14 in a binary form, see, it's a 1110. Why? Because 6 is represented as 0110, 8 is represented as 1000. Once you add this two, see, you'll have sequence of 1110 that is represented as a 14. But see, this is not valid BCD number. So once you're going to add plus 6 or the binary bits is 0110, then and then it can be converted into a BCD 14. You can see this 0110. If you are going to add with this invalid BCD number, you will have next number is 1 and 0100. So that is represented as a 14, right? So that's what the correct way of representation or conversion. So from this, if I'm going to make a complete design, you can find this added and augment that you are going to add here 6 plus 8, your Z1, Z2, Z4 and Z8. That number is having 1110, and again you have to add from here. If there is a carry, if the carry is 1, because if the number is greater than 9, see this carry out is 1 and that 1 is given to here. So here you are going to have the number 1110, and here you have to add 0110. So you have to add here plus 6, and finally from S1 to S2, S4 and S8, that sequence is the BCD sequence where you're going to get your total number is 14, right? So this is easily get the carry implementation from this particular table. Carry that you're going to get from 10 to 15 from the K map, that particular function in form of S0, S1, S2 and S3 you're going to have in form of this representation in form of the K map, and finally you are going to have the Y. Here you consider this Y is nothing but the C out condition, and that C out condition is based on S1 into S3 plus S2 into S3. By that way, see here two AND gate you have to use with the OR gate, and finally Y becomes 1. That means carry out becomes 1, and that carry out finally, if there is a 1 carry, then that will add 0110 in the next level, which is a 4-bit binary adder, right? So here you have to use 2 times 4-bit binary adder, and then you can make the BCD adder, right? So again, here we have to convert this binary into BCD. You will have a complete this truth table where you will decide the decimal numbers from 0 to 15, and your binary code is 0000, but your BCD code always you can define in form of the 5 bits. It's a 0000, right? But once the number is from 9 to 10, see it changed the sequence. So from that, if you apply the K map, from that K map for each and every output is like D0, D1, D2, D3. But in a K map, it becomes a B5, B4, B3, B2 and B1, which corresponding this one. Just you take it as a B0, B1, B2, B3 as ABCD, and you can take it as here D0, D1, D2, D3, D4 as B1, B2, B3, B4 and B5, right? So each and every aspect you can check here. All K maps are corresponding Boolean functions, like B5 is having AB plus BC, B4 is having A into B bar into C, B3 is having A bar into B plus C into B, B2 is A into B into C bar plus A bar into C. Same way B1 is equal to D, and that particular function if you are going to implement, you can check this B0, B1, B2 and B3 as such. The final D0 is like a B1 is having B0, so it's just a straight line, and after that all are following a kind of Boolean functions of the conversion. Same way you can also convert binary into XS3. You already know you have to add plus 3 always. So your decimal number is 0, binary sequence is 0000, and you have to add 0011. See, your XS3 code is 0011 up to 9. See, the 9 sequence is 1001, but if you add 3, it becomes a 12, so 1100. You convert this complete sequence in form of the K map. See, in K map, one condition if you define, and that is a X condition, and that X condition we can consider as a don't care. Why it is don't care? Because we are not taking the decimal 10 to 15 here, and this K map having the 4 literal, so it will give you up to 16 boxes. So from 10 to 15 I can take as a don't care. So from 10 to 15 mean terms, if they are either 0 or 1, I don't care, right? But for my advantage, I'm taking X condition as a 1 condition. So from that I'm going to have the E3 output is, you check the corresponding ones is available at 5, 6, 7, 8 and 9. So I can put 5, 6, 7, 8 and 9 all ones, and rest of the position I put it as a don't care, so I can consider as a 1, and from that I can be able to deduce the Boolean function E3 is equal to D3 plus D2 into D0 plus D2 into D1, right? Same way I can go for E2, and I'm going to put the 1 from 1, 2, 3 and 4 positions. So 1, 2, 3 and 4 position, and rest of the positions you can take at a don't care. And you can make 16 ones possible, no. 8 ones possible, no. 4 ones possible, yes. See, in above circuit, for reduction of E3, 8 ones possible, yes. The row number 3 and 4 are complete 8 ones possible. You can take X as a don't care condition as a 1. Same way here in a E2, you can find a don't care condition and you can take as a 4 ones. So your reduction of Boolean function of part of the E2, you can see here. Same way, you can go for E1 and E0 from this particular truth table, right? Based on that, now you have reduced this particular binary conversion into excess 3 here in form of the digital circuit. So here in form of, if you consider this particular digital circuit, where you can easily find, see, for a even, see, there are two groups having the 4 ones. So from that you can be able to find even is equal to D1 bar into D0 bar plus D1 into D0, right? Now if you particularly look for even, what are the basic logic gates are involved, is like NOT gate, is like AND gate and OR gate. So here D1 bar and D0 bar you can find from the NOT gate, but once you want to make a dot production or you want to make the dot design, you can have a kind of AND gate. In between you have a D1 and D0, again it's an AND gate, but both are connected with a OR logic gate. So even that requires all these three basic gates like AND, OR and NOT, right? Same, you can see and observe the E0. That E0 is nothing but it's a D0 bar. So it is only having the NOT gate. So by using all basic gates, AND gate, AND gate, OR gate and NOT gate, see, you can make a design that will convert binary number into excess 3, right? So from that, from your kind of conversion, what you always did, you find like 0 0 0 0, that is your sequence, and once you add plus 3, it's like 0 0 1 1. See, you have converted your binary number into 0 0 1 1, which is a excess 3, right? And throughout from 0 to 9, and even you can go further, right? But this is what a kind of design. So you, if you are making any module or any digital block that will take the input in form of binary and will give you the output in form of excess 3, see, you can design like that way. So in this particular block you have a combination of AND or an NOT gate, and that is looking like this way. So this is what about the binary to excess 3 conversion. So this is a part of the combinational circuit, and this is also a kind of code converters, right? So from this particular session you learn about the design of digital circuits of the code conversions. Thank you very much.